Hey, what's up, Math 1? This is Mr. Bainey. We're going to take a look at lesson 16.4, Reasoning and Proof. This is the last lesson of module 16. Sort of wraps up all of the geometry things that we've seen so far, including postulates, maybe some theorems about line segments and angles and things like that. So in this lesson, we look at how do we reason in math. It is a math skill in order to sort of put together our thoughts, put it in some logical order, give some reasoning or give some reasons as to why some things are true. So let's look at some vocab words. I'm not going to go too deep into these, but first is conjecture. And conjecture is sort of think of it as a hypothesis in science. We think it's true, but we're not exactly sure, so we can investigate a little bit more to see if it is true. So we can prove a conjecture is true or not. And the way that we prove is using two types of reasoning, and that's inductive reasoning and deductive reasoning. Don't worry, you won't be tested on these, but inductive reasoning sort of starts with some very specific examples, and then we go to a much more broader look at it. And deductive reasoning is just using logic or using more abstract thinking. So we're not going to look really at specific examples when we do deductive. So think of inductive as we're going very specific, and then deductive, we're going a little bit more broad or more general. Okay, so let's look at this in action. So in this Explore, part A, we're going to write a sum, remember that's to add, to represent the first three consecutive counting numbers starting with 1. So if I start with 1, then I'm going to add 2. That's the next consecutive counting number, and then the next one is 3. So consecutive means just one after the other, and the sum is 6. And part B says, is it divisible by 3? It is, yes. 6 divided by 3 is going to give us 2. Part C, write the sum of the next three consecutive counting numbers starting with 2. So if I start with 2, okay, the next three consecutive counting numbers would be 3 and 4, and that would give us 9, it looks like. And is this divisible by 3? And it is. So 9 divided by 3 is going to give us 3. So our conjecture, just by looking at those two very specific examples, you can think of this as inductive reasoning so far. The sum of three consecutive counting numbers is divisible by 3. So we're wondering if this always happens. So if I go all the way out to, 62, and then 63, and 64. If I took the sum of those three consecutive counting numbers, would it be divisible by 3? And so we want to be able to say that this is true for every single string of three consecutive counting numbers. Once something becomes true by proof, we call it a theorem because we've proved it. Remember, a theorem is something that we prove. A postulate or definition is something that we assume to be true without any sort of proof. So we're going to take our conjecture from part E, and we're going to use deductive reasoning. So we're going to go a little more abstract here using algebra. And part F, we're going to let the three consecutive counting numbers be represented by n. So n will be the first one. The second one will be n plus 1. Then think about what the third one would be. N plus 2. So the sum of those three consecutive counting numbers that I used variables for, if I take n plus the next number, n plus 1, plus the third number, n plus 2, I get this, and this becomes 3n, and then 1 and 2 become 3. So I get 3n plus 3. So we can factor the 3n plus 3, meaning we're going to sort of do a backwards distributive property. And so 3 goes into both 3n and 3. And so I can write it as 3 times the quantity n plus 1. Okay, so again, if I use distributive property, I get 3n plus 3. So you want to think of, is this, whatever this number is, divisible by 3? And it is, because if I take 3 times n plus 1, if I divide it by 3, I get n plus 1. Okay, so it's divisible by 3. 3 goes into it nicely every single time. And part J says, recall the conjecture. The sum of 3 consecutive counting numbers is divisible by 3. Look at the steps in your deductive reasoning. Is the conjecture true or false? And it is definitely true. So we're going to be looking at statements like these. Again, some of them might not be math statements, but including numbers. Some might be including geometry, and some might just be, in regular English. One important vocab word that you see down just a little bit lower is counterexample. And a counterexample is to come up with something that makes a statement false. Like if I said, you don't really need to write this down, but if I said all even numbers end with 2. Okay? This is a statement that and I could call it a conjecture if I believe it to be true. So all even numbers end with 2. This is definitely a false statement. And in order to say that this is a false statement, we just need to get a counter example. And a counter example to this would be something like the number 4. Okay? So you might be asked to come up with some counter examples to some statements. And moving on, we're going to look at some statements that we actually use already. We just don't formally write them down. So when you solve equations, you use these properties all the time. You see a long list of properties down here. So the addition property, for example, says that you can add the same number to both sides. So if you have A equals B, then you can add C on the left side and add C on the right side. And in a similar way, we also have subtraction, multiplication, and division properties. These other properties aren't used so much in solving equations. Substitution a little bit when we're dealing with systems of equations, but reflexive, symmetric, and transitive sort of work a lot more for us in geometry than it does anywhere else. Okay, and I didn't talk about this vocab word up here. Conditional statement is just a statement that has if-then. So if something is true, then the second part of it is also going to be true. So let's take a look at how we would do a proof solving an equation. And all a proof is to, if you recall some task that I give you where you have to justify or explain, a proof is more or less just explaining every single step in your process. And this is going to become tedious, but if you can practice this a lot, it's going to make the transition to doing geometry proofs a lot easier. And so in part B, we have 9 equals 17 minus 4x. So if we're going to solve this for x, the first thing that we're going to do, it looks like, is subtract 17 on both sides. So I'm going to throw this step in here so that we can kind of see what's going on. And I get negative 8, looks like. So to get to that statement, negative 8 equals negative 4x, we use the subtraction property of equality. And you know what? They actually, I don't like this fill in the blank stuff, so they actually wanted us to put 9 minus 17 there, and then we combine like terms to get our negative 8. That's why they have that extra statement there. And then the last step is to divide both sides by negative 4. Divide by negative 4, and we get a positive 2. So we use the division property of equality. And then finally, it looks like if 2 equals x, then it's true the other way around. This is the symmetric property of equality. Not something that we dwell too much on. But if you're being extremely detailed, then you could definitely use the symmetric property to state that. So down below, it asks you for the your turns to write some conditional statements, and I'm not going to worry too much about that. But I do want you to take a look at what the properties of equality are being used in number 6. So go ahead and pause it for just a couple minutes. Give these a try, and then you will see the answers in about 5 seconds. The first one here is using multiplication. We're multiplying 2 on both sides, so multiplication property of equality. Notice I abbreviated the property of equality. They're on the right side, so I don't mind if you do some abbreviations as long as I know exactly what you mean. The property of equality part is super important because when we go on to doing geometry statements, then we use properties of congruence, which is slightly different. Equality is using numbers and variables that represent numbers. The second one is symmetric property of equality, similar to the example part B above. And number 3 is substitution, because if t equals 4, that means that you replace this t right here with the 4. You do 5 times 4 plus 7, and you get 27. So you have to use substitution to arrive at that last part. And the last one is the transitive property of equality. It says that if 9 equals 4x and if 4x equals m, well, that means that 9 and m are the same thing. They're both equal to 4x, so they must be equal to each other. Okay, and we have some more vocab up here on the next page, and has to do with 2 angles that look like they're connected or they share a side. We call them a linear pair if they're adjacent angles and the non-common sides, the side that it doesn't share, are opposite rays. I don't really like to say they're opposite rays. Instead, I like to say they form a straight line. Or you can think of it as a straight angle, because a straight angle, remember, is 180 degrees. So in angle 4 in this picture, in this box, that side is a side of angle 4, but it's also a side of angle 3. So that's the shared side. And when they have a shared side, that makes them adjacent. Then the opposite rays, or the non-common sides, which is this side and this side, okay, take a look at what they form. They form a straight line, just going straight across, or a straight angle. So a linear pair are 2 adjacent angles. They are supplementary. And so supplementary is another vocab word that we have here. Supplementary just means they add up to 180 degrees. And hopefully that makes sense. So right up at the top here. So that's using the angle addition postulate. If we add 2 smaller angles together equals the big angle. So angle 3, the measure of angle 3, plus the measure of angle 4 is going to equal 180 degrees. So that's going to help us in some of the problems that we take a look at in this lesson. So this has to do with angles, but remember that we still have also the segment addition postulate, as you'll see in this example part A. This is already done for you, so you can take a look at that. Now in part B here, we know that we have angle RST is the big angle, and then angle RSP is one of the smaller ones, and then angle PST. So the measure of angle RSP is this. The measure of angle PST is this, 5x plus 10. And it tells us that the whole angle, measure of angle RST, is this right here. So I know that the measure of angle RSP plus the measure of angle PST equals the measure of the bigger angle, which is angle RST. I don't know why I wrote it up there. It's actually also down below, right here, fill in the blank. So same thing that I wrote, except that I switched the angle RST. So measure of angle RST is the biggest angle, or it's the whole angle, and that's 15x minus 10. So I'm going to go back to fill in the blank here. One of the smaller angles is x plus 25, and the other one is 5x plus 10. We just go through and we solve this. So we can combine x and 5x to make 6x, and then 25 plus 10 to make 35. Then we just go through and we solve it. 9x, if I subtract 6x on both sides, I get 9x. If I add 10 to both sides, I get 45. And that leads us to x equaling 5. So on the your turn down here, I want you to think about how you would go about doing this. I'm going to actually start off by drawing the picture for you, and then you can pause it and give it a try. So two angles, LMN and the angle NMP, form a linear pair. So linear pair means I'm going to have a straight angle. I'm doing this freehand, so forgive me if it looks a little sloppy. So I know that they're going to actually share. M is the vertex, because the way you see it's named. And then N is on the shared side, because N is in both angle names. The measure of LMN is twice the measure of angle NMP. So I know that's the bigger angle, so I'm going to put L on this side here, and I'm going to put P on this side here. Okay. So if I know what the measure of angle NMP, I'm going to call it x degrees, then I know that the measure of angle LMN is 2 times x. Okay, it's twice the measure of that angle. So I know that I'm going to have I apologize. I was going to have you try this out. So go ahead and pause it. Solution is going to show up in about 5 to 10 seconds. So the solution starts with the equation 2x plus x equals 180. Remember that the two angles, if they form a linear pair, they add up to 180 degrees because they're supplementary. Then you just go through and solve it. Now, I don't expect you to go step by step like I did, but remember that you do want to have some work shown or some thinking showed. So the equation that I have at the beginning is plenty, and you can go directly to our solution down here. And the measure of angle LMN is that one that's double the other one, so it's going to be 120 degrees. On this next page, we're not going to do much here except that I suggest you read through these postulates, very basic postulates about how points, lines, and planes work, how they intersect, what's the minimum amount of points within each of these geometric figures, and hopefully it makes sense to you. So we're going to take a closer look at these on the next page. So let's take a look at part B down at the bottom of the next page. And we need to name the results that are described, meaning it's wanting us to name some geometric figures. So we have two planes in this picture. One looks like it's going just across left to right, and the other one is going sort of towards us or diagonally. So the first thing is the line of intersection of two planes. Well, we have two planes here, and it looks like they intersect at this line right here. And so we could there's a lot of ways we can call this line. So we can call it line FG with a line notation. We can call it line M. We can call it line JG, and so on. There's probably at least a few more that we can name that intersection. And remember that because this is a line, goes forever both ways, we could also switch the letters as well. The point of intersection of two lines. So the two lines that intersect looks like it's going to be this line right here and the red line that I drew. So those two lines intersect at point J. 3 coplanar points. So coplanar means on the same plane. I believe this is the vocab word that was on 16.1, so it's a while ago. Same plane. So if I look at, I don't know, plane J, then 3 points that are on that plane could include points H, J, and F. And you can do G as well. And 3 collinear points. This is going to be on line M. Looks like that might be my only line that has at least 3 points. And the points are F, J, G. Collinear means on the same line. And looks like that's going to be about it for this lesson. Thank you so much for watching. Please refer back to the notes and the vocab words. There's a ton. And also the postulates as well as you're doing your homework assignment. Okay, thank you so much. Have a great day.